This is section 6.5, trigonometric equations. So we're going to solve some equations. I'm going to skip part 1, solving linear. We can do that in class. The other ones will show us how to solve anyway. So let's start with part 2 example. We'll do example 1. 1 plus cosine 3x equals 0. So first we want to solve for cosine 3x. Isolate the cosine 3. Oh, I'm sorry. Before we start, we want to solve over 0 to 2 pi on the interval 0 to 2 pi, and then we want to solve over negative infinity to infinity, which is called the general solution. Okay. All right. So first we want to isolate the cosine. So we will subtract 1. So we have cosine 3x equals negative 1. This gives us a good starting point. So if the cosine of 3x is negative 1, then 3x should be over 1 revolution. 3x will be pi, and that's it, over 1 revolution from 0 to 2 pi. Okay, so then the general solution for this part, notice this is 3x though, so there's only one solution on 0 to 2 pi for 3x again. Okay, so to get a general solution, we would say this is plus 2 n pi, and that takes us through infinite revolutions, positive and negative both, okay, where n is an integer. Now, we're not done solving for x, so we're not going to write that n is an integer yet, even though it is, right? So we can write that. N is an integer. I don't know if you guys have seen that. This is n is an element of the set of integers. Okay, so, but we're solving for x, so we divide each side by 3, we get x equals pi over 3 plus 2n pi over 3. Okay, and that might be written differently. It might be written 2 pi over 3 times n, or however someone else chooses to write it. And again, n is some integer. Okay, so now this is the general solution. So we found the answer for b first. To find the answer for a, you want to plug values of n for integers, right? So if we plug in n equals negative 1, this will take us to the negative values, and we don't want to start with negative values. We want to go from 0 to 2 pi. So we'll start with n equals 1. So n equals 0, I'm sorry. So for n equals 0, we get pi over 3, right? That's within 0 to 2 pi. If we try n equals 1, this will be pi over 3 plus 2 pi over 3, which will be pi. And for n equals 2, that'll add another 2 pi over 3, that'll be 5 pi over 3. And if we add another 2 pi over 3, that'll take us beyond 2 pi. So these are our solutions from 0 to 2 pi. So for letter A, from 0 to 2 pi, we have then pi over 3, pi, and 5 pi over 3. And for letter B, from the general solution, so we have pi over 3, and again these are all x equals, okay? Pi over 3 plus 2n pi, where n is an integer. Okay, so that'll be our answer. All right, let's try, and we'll leave 2 and 3 to work in class, and we'll work in those in a similar manner. The next part is solving higher degree equations. That means not linear, which means they'll have some exponent like those. Let's try number 3. Cotangent x cosine squared x equals cotangent x. Okay, so the first thing is we don't want to divide by cotangent x. Looks like we could, but because we don't know if cotangent x equals 0, then we don't want to divide by. Which brings us to another thing, and that is there's places where cotangent is undefined, right? Cotangent has vertical asymptotes 0 and pi. So we know that x cannot be 0 or pi, right? X cannot be 0 or pi. Again, this is on the interval from 0 to 2 pi. We don't need to include 2 pi because that's not included. All right, so x cannot be 0 or pi. Okay, so how do we take care of this if we can't divide by cotangent x? Well, we subtract cotangent x. So we'll have cotangent x cosine squared x minus cotangent x equals 0. And then we'll factor out a cotangent x. And then we'll separate our factors. So if you have two factors and their product is 0, then one of those has to be 0, right? So we have cotangent x equals 0 or cosine squared x minus 1 equals 0. And you can write this cosine squared x equals 1. All right, so now we can solve. So this will be cosine x equals plus or minus 1, right? So where's cotangent x equals 0? Well, that means cosine is 0. That'll happen on pi over 2 or 3 pi over 2. So x equals pi over 2 or 3 pi over 2. And this gives us cosine x equals plus or minus 1, and that'll happen at 0 or pi. So x equals 0 or pi. And remember, we can't have x be 0 or pi, so therefore that's ruled out. But we can have x equals pi over 2 or x equals 3 pi over 2. So we'll stick with those. All right, and we can always check them, by the way, so we can plug them in and check them. And again, that's something that you'll do if you have the luxury of time. Okay, so you can plug in your solutions and check to see if they give you a true statements. All right, and I'll let you do that on your own time. Okay, so we won't do it here. All right, let's try part 4 using identities. We will do part 4, number 1. Okay, and we'll leave number 2 for class. All right, so notice we have tangent x plus 1 equals secant x. Well, if this was secant squared x, then we would be able to replace with something with tangent, right? Secant squared x is tangent squared x plus 1, which kind of tells us which way to go. So what we'll do is we'll square both sides. But keep in mind, when you square both sides, sometimes you generate false solutions. As in, for example, x minus 2 equals 3. That has one single solution, but if we square it, then you get two solutions. But it turns out that for the original equation, there's only one. Okay? So when you square, sometimes you generate false solutions. But it allows you to solve like in this case. So let's square both sides. This will be, when I square tangent x plus 1, it'll be tangent squared x plus 2 tangent x plus 1 equals secant squared x. Okay? Now, if you remember your identities, your Pythagorean tangent squared x plus 1 is secant squared x. So I'll replace that. I'll say secant squared x plus 2 tangent x equals secant squared x. All right, we subtract secant squared x from both sides. We get 2 tangent x equals 0. And so tangent x is 0. Yeah. And so tangent x is 0 at x equals 0. Right? Is it also pi? 0 or pi, right? Pi. And then 2 pi, but 2 pi is beyond our 2 pi, right? Okay, so now a couple of things we forgot to check, and that is, so tangent x it'll be undefined if cosine x is 0, right? So we don't want x cannot be, where's cosine x equal to 0, pi over 2 or 3 pi over 2, right? Those are not. And secant x, that's cosine x cannot be 0, so it'll be the same thing. So tangent x and secant x are both undefined there. All right, so these are not. Now remember, false solutions, so these we have to check. So we check tangent of 0. Tangent of 0, let's see, 0, so the sine is 0 and cosine is 1. Okay, so we have 0 plus 1 equals secant, and cosine is 1, so 0 is okay. All right, 0 works. For pi, tangent of x is 0 plus 1, and secant of x, which is 1 over cosine of pi is negative 1, so it'll be 1 equals negative 1. So that one doesn't work. All right, so only x equals 0 works. So pi was we generated that extra solution. All right, let's see if we can finish the last part, and that is this part right here. We're going to do part B. We're going to find an exact solution in radians and then give approximations in degrees rounded to 1 decimal place. So let's try number 1, cosine x equals 0.6. Now, if you remember your unit circle, we don't have an exact value for that. Okay. In fact, if we try using cosine inverse of 0.6, let me see, 0.6 inverse cosine, I get 53.13 etc. degrees, and if I do it in radians, I get 0.92, etc. So it's a never-ending decimal. All right. So for the exact solution from 0 to 2 pi, give exact solutions over 0 to 2 pi in radians. Oh, okay. So cosine inverse of x, of 0.6, right? And then where is that? So 0.92 something radians. Again, let's think about the unit circle. So 1 radian. This is like 1/3 of a pi, right? So this is pi radians, which is 3.14 radians. So 1 radian is about in this quadrant right there. Okay, so that's cosine inverse. Yeah, and if we look at the that's not the only place that has cosine x equals 0.6. Now notice we use cosine inverse, but cosine inverse just gives us one answer. There's another point down here that also has cosine of it equals to 0.6. And how do we write this if we have we're using this kind of notation? So I think I'm going to stop here. Yeah, let's pause it here and we'll finish on the other one because we have a lot to talk about. So we'll pause part 1 here, and then we'll start a part 2 and finish off this problem on the second video for this section. Okay.